Python is fundamentally an abstraction over C. We operate primarily in CPython, the language's reference implementation, and the reason we all have trust issues with performance. When you write code, it is not executed directly. Instead, it is compiled into bytecode, a binary intermediate representation stored in .pic files, those little ghosts that haunt your project folders. The Python Virtual Machine, PVM, is a stack-based machine that processes this bytecode. When a function is called, the PVM creates a frame object containing the local namespace, the bytecode instructions, coplatch code, and the evaluation stack. The execution cycle involves a continuous while loop that fetches the next opcode, evaluates it, and advances the instruction pointer. The fundamental bottleneck here, the elephant in the room, is the Global Interpreter Lock, GIL. Because Python's reference counting is not thread-safe, the GIL ensures only one thread executes bytecode at any given time. For CPU-bound tasks, this prevents true parallelism, effectively turning your 16-core workstation into a very expensive space heater. To bypass this, you must use multiprocessing, which spawns separate memory spaces, each with its own PVM, its own GIL, and its own existential crisis. Python is a bit of a hoarder. It does not always return memory to the OS. It uses pmalloc, an allocator optimized for objects smaller than 512 bytes. Every object is a PyObject struct in C containing its reference count. Basically, how many friends do I have counter. When this count hits 0, the object is immediately deallocated. However, we face the reference cycle problem, where two objects reference each other, keeping counts above 0 indefinitely, like a toxic relationship that won't end. The generational garbage collector, GC, solves this. Objects start in generation 0. If they survive a GC cycle, they move to Gen 1, then Gen 2, graduating through the ranks of survival. The GC triggers based on specific allocation and deallocation thresholds. To optimize memory, use post slots in your classes. By default, every instance has a dict or hash map for attributes, which consumes memory like an open buffet. Using slots forces a fixed-size array allocation, drastically reducing memory overhead for high-frequency objects and making your RAM much happier. Welcome to the magic of Python, where we start playing God with the syntax. A descriptor is any object that defines and get, set, or delete. When you access an attribute, Python invokes the descriptor protocol. This is the wizard behind the curtain for decorators like @property, a class method, and @static method. Meta classes are the classes of classes, the stuff of architectural nightmares. When you define a class, Python creates the class object by calling type, name, bases, dict. A custom meta class intercepts this process. By defining new twice in a meta class, you can inspect or modify the class dictionary before the class object is even created. This is how frameworks like SQL Alchemy or Django auto-register models or enforce schema validation at definition time. It's incredibly powerful, and if you use it wrong, you'll be the only person in the office who understands why the code works or why it's currently on fire. Stop using standard for loops for large data sets unless you enjoy watching your progress bar move like a snail on sedatives. A list comprehension is eager. It allocates the entire list in memory immediately. Conversely, a generator expression is lazy. It's the "I'll do it when I feel like it" approach to coding. It returns an iterator that computes the next value only when next is called. The yield keyword pauses the frame, stores the local state, including local variables, and returns control to the caller. This allows for constant memory complexity, O1, even when processing millions of rows. It's the difference between carrying a whole warehouse on your back versus taking one box at a time. When nesting data, yield from, provides a clean interface for delegating to sub-generators, maintaining the call stack efficiently without unnecessary overhead or mental gymnastics. Python uses the C3 linearization algorithm to determine the method resolution order, MRO. In complex diamond inheritance, where your class structure looks like a family tree from a confusing soap opera, C3 ensures that parents are visited before children and in a predictable order. You can inspect this with class name, MRO. Always use super for cooperative multiple inheritance. Crucially, super does not simply point to the parent, it points to the next class in the MRO, which might not be who you expect. Regarding encapsulation, Python has no true private members. It operates on the consenting adults policy. Double underscores trigger name mangling. The interpreter renames the variable to avoid accidental overrides. It's a keep out sign, not a locked vault. If someone wants to break in, they can, but they'll have to feel guilty about it. For high-scale systems, the transition from script to application requires event loop mastery. The Asyncio library manages non-blocking IBAMO. By switching between coroutines when one is awaiting a network or disk resource, basically multitasking while the slow stuff finishes. Performance is not guessed, it is measured. Don't just feel like your code is slow. Use cprofile for deterministic profiling to find the total execution time, and line profiler for row-by-row timing to find that one line of code that's ruining your life. Finally, packaging matters. Tools like Nuitka or PyInstaller compile your bytecode into an executable. This wraps your dependencies and the CPython runtime, allowing you to ship a standalone binary, the standard for production-grade, platform-independent software deployment. Now go forth and code responsibly. Please like and subscribe.